right now. If you are watching us on Now Media TV, it is May 6th, 2023, unless you're watching a rerun. I'm here to tell you that right now the moon is being annoying. One of the nicer small meteor shows is going on, the Eta Aquarids. Normally, I'd be recommending you go out, look up, and enjoy a spring sky decorated with up to one meteor every minute or so. But the moon, right now, it's full, it is bright, and its light is going to drown out most of the show, at least to your eyes. We can observe our skies in a lot of different ways, and if you have an old FM radio hanging around, try this. Later tonight, tune the radio to some frequency between the stations, someplace where all you normally hear is static, and then just leave it on and listen. You should periodically hear a whistling sound. That eerie noise comes from radio signals from somewhere here on Earth reflecting off the meteor's path. Meteors are generally created by pea-sized or smaller grains passing through our atmosphere. As they burn up in the sky, they ionize the air around them, and radio signals can bounce off that ionized trail. So, while the moon overwhelms the show for your eyes, go listen to a meteor shower. The Eta Aquarids are best experienced around 2 a.m. local, and this storm is ideal for folks near the equator or in the southern tropics, but it's still good for those in the mid-US and southward. And when you do hear or see a meteor, know that you're observing a bit of Comet Halley. This year, Earth's orbit is crossing the path Halley left in 390 before the Common Era. That's like 2,000-year-old dust we're seeing. But before you go, like I said, we have a full show. We're going to be talking more about meteors, including the source of the Geminid meteor shower, asteroid Phaethon, as well as hot planets, hungry black holes, and how we're working to uncover the identity of dark matter. All this and more is coming at you right now, right here, on Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Space is weird. Full stop. Nothing more, nothing less. Space is weird. Case in point. Every December, the week of my birthday, there is a meteor shower called the Geminids. Most meteor showers are associated with the paths of comets through our solar system. As they orbit through the inner solar system, these hunks of mostly ice with bits of rock and dust, they get melted by the sun and give off gases, dust, and even materials like sodium. That meteor shower in December, however, is different. Back in 1983, researchers tracing back along the dust trail found not a comet, but an asteroid. And that asteroid, named Phaethon, has left astronomers very scientifically guessing. Researchers thought that as the asteroid gets near the sun, it leaves behind a trail scorched off of dust. In 2009, the stereo mission spotted a short tail from Phaethon when it was closest to the sun, and these observations were repeated in 2012 and 2016. This could have been case closed, except in 2018, the Parker Solar Probe's better cameras were able to see that Phaethon was actually giving off far more material than could be explained by scorching off dust. So, we have an object that doesn't appear to be icy and is giving off material, and that material can't be just dust. With the simple answers ruled out, our sleuths asked, what else is possible? And for inspiration, they went back to the comet ingredient list. A common ingredient in comets is sodium. And in addition to seeing comets with sodium tails, we also see a sodium tail coming from the planet Mercury. And lucky enough for the researchers, another mission, the SOHO mission, has a sodium filter. SOHO's primary mission is to observe the sun, but during 18 orbits between 1997 and 2022, Phaethon just happened to wander straight through SOHO's field of view. Sure enough, Phaethon shines bright in sodium filters. These results are published in a new paper in the Planetary Science Journal, led by Qiuxing Zhang. And these results answer a whole lot of questions, but they also raise a new one. It's easy to imagine that an object leaving behind a trail of dust will also leave behind a trail of larger bits that we see as a meteor shower. But sodium? Sodium isn't chunky like that, at least not in this situation. According to Zhang's team, there may have been a disruptive event a few thousand years ago, perhaps a piece of the asteroid breaking apart under the stresses of Phaethon's rotation caused Phaethon to eject the billion tons of material estimated to make up the Geminid debris stream. One mystery solved, and one much, much more interesting question raised. As I said, space is weird. In fiction, authors often resort to making up particles, substances, and science in general when they want to make things sound particularly spacey. But there is enough real stuff that you really don't have to make anything up. Consider the planet Kelt 9b. This soon-to-be-blasted to smithereens planet is snuggled up right next to an extremely hot star. Its surface is actually heated to 4,000 degrees Celsius, which is the temperature of a pretty average smaller star. Discovered in 2016, this planet is proof pretty much any star can have a planet, and not all planets get to live very long. In a new paper in Astronomy and Astrophysics, researchers take advantage of these high temperatures to look for high atomic number atoms. This kind of a superheated planet lets us see heavier elements than we can detect around cooler planets. The only way we can detect atoms in alien atmospheres is for those atoms to be in a gaseous form. And let's face it, even on Mercury, metals are lumps, not gas. With Kelt 9b, titanium gets to be a gas, and iron and chromium, nickel, scandium, barium, and I had to look this one up, terbium. With 65 protons in its core, this heavy metal lives in that cast-off block of elements beneath the main part of the periodic table. Technically called rare earth elements, terbium on Earth is almost exclusively mined in Banyan Obo in Inner Mongolia. And now we know of one other place in the universe where it can be found, the planet Kelt 9b, as a gas in the planet's atmosphere, along with chromium, gas. Space is weird. But weird is just another word for different. The things we've decided are normal here on Earth are only normal here. And if we want to figure out how to live out among the stars, or at least on other worlds in our solar system, we're going to have to get used to some new normals. Currently, it looks like the next destination for humanity beyond our moon will be Mars. Over the years, that has fluctuated. So if we end up going to an asteroid instead, don't at me on whatever replaces Twitter someday in the future. Part of preparing for Mars is understanding the red planet's structure on the outside and inside. With the InSight mission, researchers were able to collect nearly 4 years of seismic data. Here on Earth, the constant motion of the continental plates leads to regular large releases of seismic waves. As we discussed last week, differences in how the waves move through different parts of the planet allow us to measure our Earth's interior in spectacular detail. Fortunately, or unfortunately, Mars doesn't have continental plates, and it doesn't have the same constant rumble of quakes. But it does have some quakes, and its thin atmosphere lets far more asteroids reach its surface where they can shake things up. And in 2021, just a month apart, both a quake and an asteroid struck the side of Mars opposite from the InSight mission. These two events were the only two events large enough and far enough away to allow researchers to map the inside of Mars. In a new paper in the Proceedings of the National Academy of Sciences, researchers led by Jessica Irving were able to measure a largely liquid iron alloy core with sulfur and oxygen at Mars. This liquid core is in contrast to our planet's solid core, which is surrounded by a liquid shell. Between its structural differences and its small size, Mars' internal structure just can't generate a powerful magnetic field like our Earth's core can. And without a magnetic field, solar wind constantly blows away Mars' atmosphere, while solar radiation and cosmic rays rain down on Mars' surface. So, if you want fewer quakes with a greater risk of radiation and asteroid fall, Mars is the place to be. But if you want a protective magnetic field and quakes and fewer asteroid impacts, Earth is the place to be. After a break, we're going to look at more weird things in space. Stay tuned for messily eating black holes, their jets, and the fluffy rings they sometimes wear. Stay tuned. Last week, we brought you news of a newly processed image of light from around the central supermassive black hole in the galaxy M87. That was a radio image, and it showed us this galaxy's innermost region in superb detail. This week, we zoom out a bit and look at the system using millimeter wavelength observations to see the material both streaming into the black hole in a tight, bright ring, and also the material being expelled back out through a jet. This data comes to us through the combined observational powers of the Global Millimeter VLBI Array and the Atacama Large Millimeter Array and the Greenland telescopes. The image itself is rather unimpressive, and it takes an artist's illustration to really breathe life into the science. What we're seeing is material falling into the black hole and ending up in a disk as it drops angular momentum, heats up, and eventually falls in. This hot disk is filled with charged particles that generate a massive magnetic field as they orbit. This magnetic field can expel electrons and other material out as jets. According to Thomas Kirkbaum, one of the researchers involved in this study, which appears in Nature, quote, "With the greatly improved imaging capabilities by adding ALMA and GLT into GMVA observations, we have gained a new perspective. We can see how the jet emerges from the emission ring around the central supermassive black hole, and we can measure the ring diameter." End quote. And that diameter isn't what we expected. Researcher Kazuro Hada explains, quote, "The radiation from the inner region close to the black hole is broader than we expected. This could mean that there is more than just gas falling in. There could also be a wind blowing out, causing turbulence and chaos around the black hole." End quote. In the press release, they describe the result of this inflow, outflow, and turbulence as a fluffy ring. With every observation and every new wavelength, we learn a little bit more about this nearby supermassive black hole, its eating habits, and how it distorts space and time. M87's supermassive black hole is truly huge. and we're able to see it doing things at huge distances. A much smaller, but still millions of solar masses, supermassive black hole lurks in the center of our galaxy. And looking around the galaxy, we also see black holes from individual massive stars that have died and collapsed down. What lurks between the stellar mass black holes and the supermassive black holes, however, is a bit unknown. There should be lots of intermediate-sized black holes with hundreds to tens of thousands of solar masses, but we are so far struggling to find them. But what we can't find in the sky, we can at least model within computers. And a study led by Fulya Kiriju has now shown what happens when an intermediate mass black hole interacts with a star. Per their press release, when a star approaches an intermediate mass black hole, it initially gets caught in the black hole's orbit. After that, the black hole begins its lengthy and violent meal. Every time the star makes a lap, the black hole takes a bite, further cannibalizing the star with each passage. Eventually, nothing is left but the star's misshapen and incredibly dense core. At that point, the black hole ejects the remains. The star's remnant flies to safety across the galaxy. This is the kind of event that I have to admit I really want to see. Kuroji explains, quote, "We found that stars undergo multiple passages before being ejected. After each passage, they lose more mass, causing a flare of light as it's ripped apart. Each flare is brighter than the last, creating a signature that might help astronomers find them." End quote. So we watch, we wait, and hopefully we will someday see if these models can be proven through the flickering light of a dying star. Every night, countless objects flicker, flare, and wink out in the night. A few telescopes scattered about the planet are actually dedicated to catching these changes, called transients. And sometimes it takes a bit before humans can process all those robotically captured events and understand what is going on. According to a press release from Purdue University, one of the most luminous, energetic, long-lasting transient events didn't blaze through the night sky, inspiring legends and launching civilizations. Instead, astronomers acting as celestial super sleuths uncovered evidence of the star's death throes, where it had hidden undetected for years in a mass of computer-gathered telescopic data. Captured by the Zwicky Transient Facility in California, this high-energy event in 2020 released more than 1,000 times the energy of your typical supernova and is among the most powerful events seen in the sky. Its distance of nearly 8 billion light years allowed this massive amount of light to appear as a mere flicker in the sky. It would take an advanced computer algorithm, the recommender engine for intelligent transient tracking, to look through the data from the Zwicky Transient Facility and other scopes to find this object. According to Bhagya Subrayan, the first author of a new paper in the astrophysical journal Letters, we think a very supermassive black hole pulled in a star and ripped it apart. The forces around a black hole, called tidal disruption, pull other objects apart in a process called spaghettification. We think that's what happened, but on extreme timescales. The most massive of black holes ripping apart a massive star. The duration is unlike anything we've ever seen before, and it produced the most luminous transient in the universe. End quote. It's a black hole eat star universe out there, where it takes 100 days for the eating to happen. It doesn't happen a lot, but when we look at enough of the sky, we can see even the rare stuff hiding in the data. And black holes aren't the only objects out there ready to eat a snack. We've long known that stars like our sun will expand in size in the latter parts of their evolution. Looking around the galaxy, we see objects that formed with masses similar to our sun but have already expanded. We know from statistics and models that up to several stars a year make a great expansion, but catching those few stars in the act out there among all the billions of stars in the sky has so far been a challenge that eluded us. Until now. The Zwicky Transient Facility spotted a short-lived optical outburst in 2020. An analysis of NEOWISE data revealed that a long-lived infrared glow was also associated with this spot. According to a new paper appearing in Nature and led by Kasala D., the resulting light curve and spectra share striking similarities with those of red novae, a class of eruptions now confirmed to arise from mergers of binary stars. Its exceptionally low optical luminosity and radiated energy point to the engulfment of a planet of fewer than roughly 10 Jupiter masses by its Sun-like host star. To see this system in detail, the team used the discovery data to get time on the Gemini South Observatory. This massive telescope was able to see how the star not only consumed a companion, but also burped out 33 Earth masses of hydrogen and 1/3 of an Earth mass of dust. According to team researcher Ryan Lau, quote, "That's more star and planet-forming material being recycled or burped out into the interstellar medium thanks to the star eating the planet." End quote. Put another way, we are all made of stardust. But some of that stardust has already been recycled through planets, so we're made of atoms formed in stars and recycled through planets and other stars and who knows what else. We are highly recycled material. After the break, we'll be back to take a closer look at how we understand our universe and how it's evolving over time, or how we don't understand it. There is a lot we don't understand yet, and that's why we do science. Stay tuned. One of humanity's oldest quests has been for an explanation of all that is and how it got there. From the creation stories of every culture to the ever-evolving quest for a scientific theory of everything. Over and over, people have tried to find that one true answer. And a satisfying answer just hasn't been in the cards. Currently, we look at the universe from the perspective of two different standard models. On one side, we have the standard model of particle physics, and on the other, the standard model of cosmology. The standard model of particle physics describes how all matter is built of fundamental particles, things like the electron, quarks, neutrinos. This theory doesn't have an underlying explanation for why what we see is what we see, but the experiment-based understanding that has been built up over the past 150 or so years is thus far able to make predictions of new particles and explain what we should see known particles doing. Over the decades, folks have put forward theories that expand out the standard model to add new particles and new underlying reasons why what we have is what we have. But our experiments have so far failed to find evidence for any of these greater theories. And so we're in this awkward situation where we're experimentally measuring a whole bunch of stuff, building up a really nice picture that is only missing a couple of pieces, and we have no idea why the picture looks like this. And if the stuff missing from the theory can fill in the missing 85% of the universe's mass. That missing 85% is dark matter. We know the universe is largely composed of stuff we haven't been able to detect except through its gravitational pull. When we look at massive galaxy clusters colliding, we can see the light of background objects getting distorted by the gravitational pull of the cluster's dark matter. These distortions let us map the dark matter and start to make some estimates about its nature. For instance, these maps show us that while the stuff of galaxies, gas, stars, dust, may pile up and interact during a collision, the dark matter simply keeps moving like the contents of a pickup when a truck comes to a crunching halt. Scientifically, we say that dark matter is collisionless. This means that you can crash clouds of dark matter together, and the probability of any two particles colliding is so low that you can actually expect to see no interactions. This leads us to think dark matter, at least in part, is made of stuff, particles of some sort, that we just haven't found. We've discussed some of the possibilities on this show before. Sterile neutrinos are the possible explanation I'm watching most closely. If they exist, these particles could weigh hundreds of thousands of times less than an electron. Other folks have postulated there are weakly interacting massive particles out there with masses thousands of times larger than the mass of an electron. Yet others think that dark matter could be composed of axions, particles we've never seen but that are predicted by the Standard Model. These particles are needed to allow the kinds of particle interactions we see to take place. The particles, like neutrinos, should be extremely lightweight. And here's the thing. Dark matter doesn't have to be just one of these things. It could be a little of each with a handful of small black holes thrown in for flavor. To figure out what dark matter is, we really need to keep looking for signs of what it does, like the way it bends light, and we need to see if we can learn more than it's collisionless. And this is where we have to start looking at everything from relativity to the Standard Model of cosmology, which explains how our universe expands from a single point to everything we see today. Let's take this one step at a time. Einstein's model of gravity with relativity predicted that light bending around a large mass can allow us to see the same object multiple times. This is because light that was meant for one part of the universe gets bent toward us, allowing us to see both the direct light and the bent light. Exactly how the light is bent and how many different times it gets bent our way is determined by how the mass is distributed. Weakly interacting massive particles, they should have a smooth distribution that is dense near a galaxy or cluster center and then decreases smoothly. Ultralight particles like axions would exist in such large numbers that the wave part of their wave particle nature would cause them to interfere with each other, causing crinkles in their density pattern instead of that nice smooth distribution the WIMPs get to have. In a new paper in Nature Astronomy led by Alfred Amruth, researchers directly compare observed gravitational lenses with what is expected from systems dominated by WIMPs or ultralight particles like axions. The ultralight particles, they're the match. What we see is not explained by massive particles and their smooth distribution. As co-author and Nobel Prize winner George Smoot puts it, quote, "Understanding the nature of particles that constitute dark matter is the first step towards new physics. This work paves the way for future tests of wave-like dark matter in situations involving gravitational lensing. The JWST should discover many more gravitationally lensed systems, allowing us to make even more exacting tests of the nature of dark matter." End quote. Smoot is correct. This result needs to be confirmed by looking at more systems. But this is a start, and there are other things we need to look at as well. Consider the growth of galaxies and galaxy clusters. When theorists build models of the universe, they assume that particles flying through the universe have a variety of speeds. Things that are moving slower are called cold, and things that are faster are called hot. cold material can readily clump together, building into large, stable structures. Hot material, it smooths everything out, mixing it up and preventing structures from forming. In theory, in many theories to be accurate, WIMPs are a form of cold dark matter that facilitate the rapid growth of structures. Neutrinos, in general, are an ultralight particle that is generally thought to be hot, and in some cases, neutrinos are actually observed zipping along at close to the speed of light. Assuming sterile neutrinos, which we presume could be dark matter, aren't too different from the neutrinos we already know, they'd be hot. But axions, they seem to be a Goldilocks of a particle. They are cold, they fit what we seem to need, and they leave space for neutrinos. A combination of axions and neutrinos would actually allow us to tune how hot or cold things were and match exactly what we see. And what we see is the rapid growth of structure in the early universe. The more the JWST peers into the depths of space, the more objects it is finding that are shining at us from just a few 100 million years after the Big Bang. In a new image released April 24th, scientists can make out the light of 7 distant galaxies that are gravitationally bound together. We're able to see these 7 systems thanks to the gravitational lensing of a much closer cluster of galaxies. This crowded field of galaxies that are near, far, and very, very far away, and everything else in the field. It's possible that as we observe this mess more, we're going to discover more. But as it stands, those 7 galaxies demonstrate the galaxy clusters had already begun to form when the universe was 650 million years old. Over time, researchers believe this kind of a tiny knot of galaxies will gravitationally pull in more and more material. If we could see this system as it appears today, it would likely be as massive as the Coma cluster of galaxies. With JWST, we're going to be able to measure, thanks to the finite speed of light, exactly how mass went from the mostly smooth distribution we see in the cosmic microwave background to the lumpy, large-scale structure of today. The further away we look, the longer it takes the light to reach us. When we look at the nearby Andromeda Galaxy, we see a system as it appeared when light departed it 2.5 million years ago. The further away we look, the further back in time we look. And thanks to geometry, the further away we look, the larger a volume of space we can see. I am hopeful that in this decade or the next, we're going to be able to say, dark matter must have been this temperature, this cold, or this hot, to create the universe we see evolving across time. And with that information, I'm also hopeful that we'll understand just what mix of potential particles is making up dark matter and so far avoiding detection. And that standard model of particle physics, it has room for both these particles already. No underlying physics understanding required. I feel that the mysteries of that underlying physics, if it's there, is what will be around for a whole lot longer, keeping physicists and probably some philosophers awake late into the night. This is why we do science. After the break, we'll be looking at the past week's wild ride of launches and aerospace news. Stay tuned. This week, we have so much news about spacecraft that I'm just going to go straight to welcoming on aerospace correspondent Eric Mattis for this week's Tales from the Launch Pad. Hey, Eric.
Hi, Pamela. As we were getting ready to record last week's episode, SpaceX launched a Falcon 9 carrying the second pair of O3B M-Power satellites for SES from Cape Canaveral Space Force Station. SES is building a medium Earth orbit next-generation broadband satellite constellation. With these 2 satellites, they are just 1 launch away from being able to commission their MEO constellation. The full constellation will consist of 11 satellites and be able to provide a throughput of several gigabits per second. It will take a few months for the satellites, which have all-electric propulsion, to get into their proper positions. They join their first pair of O3b M-Power satellites that were launched last December. The next pair of satellites are scheduled to be launched by SpaceX by the end of the year. On May 1st, Universal Time, a Falcon Heavy launched from Launch Complex 39A at Kennedy Space Center, carrying several payloads directly to geostationary orbit. This feat is rare. Even less common is commercial satellites getting the privilege. Such an expense is typically only seen with large government spy satellites that need to get operational very quickly without giving adversaries time to track them in intermediate orbits, or are so specialized they do not have large propulsion systems. The primary passenger on the flight was Viasat-3 Americas, a 6.5 metric ton beast of a communications satellite that will, you guessed it, provide communication services to the Northern Hemisphere. It is expected to do this for 15 years, a typical lifespan for ComSat. It also has electric propulsion. The other satellites are much smaller. Arcturus is a 300 kilogram satellite that will bring broadband internet to Alaska, the first satellite dedicated to a single U.S. state. In this role, it will be called Aurora 4A, but the company who makes it hopes to sell capacity to other customers as well. The final and smallest satellite in the Falcon Heavy's payload fairing is called G-Space One. G-Space One is for a U.S. company called Gravity Space. It has several purposes. The main one is to act as a surrogate for a few Indonesian communication satellites that haven't launched yet, keeping their frequency allocation active. The UN organizes slots in geostationary orbit through its organization, the International Telecommunications Union. They have this authority under the UN Space Treaty. The problem if a company loses their slot is twofold. These slots are limited because of possible interference with neighboring satellites and are given to nation states. Private companies that want to operate in these slots must petition the country, or buy at auction, these slots. They can get expensive, up to the tens of millions of dollars. The slots are only held by the AGU for a certain amount of time. If the company can't get a satellite in service, the slot goes back into the pile and another country can get the slot. This is particularly important for a country like Indonesia, which has a large and growing population in need of communication. The country is also relatively small, so they don't have many slots from the ITU. So every satellite matters, and most are given to big companies that have the technology to operate multiple satellites in one slot, which requires careful coordination on downlink. The delayed satellites will be operated by Indonesia's flag ComSat operator, Pacific Satellite Nusantara. Those two satellites? They will be launched later this year on a pair of Falcon 9s. The reason they are so delayed is because Indonesia could not secure funding to have them built. G-Space One also has a camera system to track other objects in geostationary orbit called Orbit Guard. It is the first CubeSat to operate in geostationary orbit. To accommodate all these payloads and the significant amount of energy needed to get them where they needed to go, all three boosters of the Falcon Heavy were expended, the first time SpaceX has done this. The fairings were recovered though, almost 2,000 kilometers downrange of the launch site. SpaceX posted a video taken by camera on one of the fairings showing the plasma trail of its reentry on social media. According to the text with it, the fairings hit the atmosphere at over Mach 15. Also, there was another Starlink launch, of course. Unlike last week, weather was on SpaceX's side and the mission launched on May 4th. This one was from the Cape and carried 56 of SpaceX's normal-size Starlink 1.5 satellites into orbit. The booster was Booster 1069 and landed on the drone ship Shortfall of Gravitas. The fairings were recovered as well. We keep track of orbital launches by launch site, also called Spaceport. According to RocketLaunch.live, so far this year, the USA has had 33 launches, China 17, Kazakhstan 4, India 3, Japan and Russia each have had 2, and French Guiana, Israel, New Zealand, and the United Kingdom each have had 1. Of those 65 launches, there have been 4 failures, reminding us that space is hard.
Thanks, Eric. Before we go, I have an update on the New Horizons mission. Launched in 2006, this high-velocity spacecraft flew past Pluto in 2015 and the Kuiper Belt object Aerocuth in 2019. And today, the mission continues to journey through the Kuiper Belt and toward the edge of our solar system. Last week, Marcia Smith of the Space Policy Online reported that New Horizons has been extended for 2 more years, but during that time, NASA will only be funding the mission to do heliophysics. According to Alan Stern, the mission remains healthy, and we all hope that it will be able to continue well beyond those 2 years. This means that as we approach the Sun's most active period in its current cycle, we're going to have one mission looking back to see how the Sun's temper tantrums can affect the entirety of our solar system. If you want to join in on observing the Sun's activity, check out spaceweather.gov and learn when aurora may be visible over your corner of the world. That's it for now. Good night, everyone, and remember to go out and look up.